Hello everyone and welcome to Handmade Hero, the show where we normally code a complete game live on stream, but during the pre-stream today I kind of got riled up, as I sometimes do, talking about how bad modern hardware and operating systems have gotten. And it reminded me that I did have a lecture on this topic that I never recorded, and so I kind of wanted to just go ahead and record it. Now, I do apologize because normally what you would do with a lecture, and what I do with a lecture, is rehearse it first, unlike Handmade Hero, which is just seat of the pants by design and by intent. Normally a lecture is much better if rehearsed, and I did rehearse it when I gave it the first time, but I think it was something like 6 years ago. And so I suspect that this will be pretty rough, but I wanted to get it out there just so I could have the material for reference. Anyway, this lecture is called the 30 million line problem, and it is a lecture about the dangers of how we have let hardware and operating system design kind of run away and become untenable. Without further ado, let me just jump right into it. It's not a particularly long lecture. I think it's meant to take about 30 minutes. All right, so one thing that we can all appreciate, and that I think is always the starting point for discussions like this, is just an appreciation of the extreme difference between the kinds of hardware that I had when I was a child, or whenever you were a child, or the hardware you can first remember, and the hardware you get to program today. And the fact that that says 2015 on there, I'm guessing that's when I first gave this lecture, so 3 years ago, I guess. This would be even higher today. And so when I look at these two things, that 2015 there, that's the machine that we were programming Handmade Hero on. And that machine was actually a 2010 machine. So the machine was actually 5 years old at the time that I'm talking about it. And that's what I was programming on in 2015. Nowadays on Handmade Hero, we actually updated to a machine that's way, way more powerful than this machine. So it's worth pointing that out. But if you look at these two, in 1990, my processor was 25 megahertz. It was an Amiga computer, it was 25 megahertz. And now in 2015, not only are the speeds, 100 times faster, that 2.8 gigahertz, right? But there are also more of them. So you don't just have one processor anymore for a CPU. You've got 4 of them, effectively, in that particular machine. And each one of them also has 4 wide ALU units, right? It can actually issue 4 times. Now the ALU units are 8, sometimes 16 wide. And you have hyperthreads as well. And the core counts are going up above 4. It's just, there's an orgy of hardware in there. Obviously the graphics was way simpler back then, 320 by 512 by 5 bits per pixel. Now we're up to, this at a minimum. And that was, like I said, on a much crappier machine than the one now. So 4K displays are common now as well. The number 6 and the number 8 are very close for memory, only the power of 1,000 has changed. It's gone from megabytes to gigabytes, right? And not only do we have more memory by a factor of 1,000, but we even have that memory on 2 different processors. So you have that much memory on your main processor and on your graphics processor. In 1990, it was shared between the two. And of course, hard drives are absurd. I don't even want to go into those, right? So when you look at that picture, really all you can say is, at least from the strictly density side of things, hardware developers have delivered fantastic gains in the past 25 years, now 28 years. However, the software that we use is way worse than it's ever been. The experience using the computer in 2015 or today, 2018, compared to what it was like using it back when on the computer that I was referring to before, the computer I was using before was a very serene and pleasant experience. The only time it really ever became frustrating was the CPU didn't even have memory protection. So when you were programming an application, you might introduce a bug that would overwrite some memory and cause your operating system to crash, right? And that was really unfortunate. And nowadays, we are fortunate enough to have CPUs that have virtual memory protection, and they don't have to have this problem anymore. So that's great. So we fixed one problem, pretty much the only problem that we used to have back then. And in exchange for that one fix, unfortunately, for whatever reasons, our software has become almost unusable. And it's unusable in many, many, many different ways. These are just some screenshots of things I see every day, basically. These are not uncommon. They're my common experience using a computer. The Twitter is over capacity fail whale I don't think shows up very much for me on the desktop anymore, but amusingly, I now for the first time have an Android phone. I didn't have a smartphone for a long time. I got an Android smartphone recently, and it cannot ever load Twitter from a URL. If you go to twitter.com, it just says Twitter is taking too long to load in a little message, and no matter how many times you refresh it, it'll never load. You have to like go back to the title bar and reforce it to reload the page, and then sometimes it will work, right? So even that one that maybe sort of got fixed really didn't, because now we just got the other ones. So anyway, when you use software today, what you generally see is a huge array of viruses and software instability and updates that happen when you don't want them to, and message boxes that pop up that you can't control, and your operating system rebooting and losing work and doing all these other sorts of things. Even the hardware now has failure designed into it. You try to plug into things to play video from your computer to your television, and it turns out you can't play it because some weird like HDCP thing has decided that even though you are using a legitimately purchased Blu-ray on a legitimately purchased television, it just doesn't work, right? And this is really frustrating. It causes such a loathsome experience with a personal computer that you just want to throw the thing out the window a lot of times if you do anything at all with your computer that isn't just checking Facebook once in a while. And even that can become kind of frustrating. And sometimes these things aren't just frustrating, they're actually really detrimental, right? And there was some kind of absolutely ridiculous thing in the news back on the day or close to the day when I was doing this lecture originally. You could go find new ones today. They happen all the time. But this was a kind of funny one, headline that you read, and it's like something was going on where you needed a computer to actually work in order to do something for a real world consequence, and of course Windows Update or something decided it needed to update and they couldn't use the computer, and then they ended up in a situation that actually cost them something significant. And you read all these funny stories, but it's not funny, right? Like, that's just not that funny when you actually think about how bad computing has failed when ostensibly it's come so far. The hardware that they were using for whatever this situation is was so much better than the one that I was talking about in 1990, yet this never would have happened in 1990, right? And so one of the things that I think we need to step back and think about is, why is software so much less reliable and so much more unpleasant to use today than it was? It should be much more pleasant to use today. The hardware is so much better, and it is so much easier to get reasonable performance out of it that you would think that these applications are simple. Remember, these are applications that are oftentimes very close to identical to the ones we were using. A word processor on, say, an Amiga computer from 1990 and a word processor of today, the performance requirements aren't that different, actually, right? And yet, the one running on the thousands and thousands of times faster machine is somehow still as slow or slower when you're actually trying to type things into it and it's laying out the text, you know? And so we have to think about why, if it should be so much easier to make software today, why is it actually seem to oftentimes not get any better? Although we do add features over time, certainly, the experience doesn't seem to get much better, and also all of these other aspects of the experience that are horrible all of a sudden start coming in. Why are there all these long load times and spinning progress bars that never seem to complete, and crashes and all these other things? Why are all of these things seeming to be more rampant rather than less, when we should be having an easier time, right, with making the software, and more of our focus, it should be easy to have more of our focus spent on reliability and all this sort of stuff, because we're doing fundamentally, hopefully, less work to make a reasonably performant experience for the end user. That's what we would think. Well, I would posit that the reason is actually very easy to understand. I think the reason is simply that since things are no longer coded from scratch, from start, what we end up doing is we just pile code on top of code on top of code, right? And so anything that might have been problematic or wrong about any underlying layer and that could interact with any other layer that we put on top of it, they all just keep multiplying together to multiply out in almost an exponential fashion our failure rates and our performance problems, right? And what I've done here is I've constructed a graph of operating system, just the operating system, nothing else, over time. And what you can see here is that the operating system back in 1991, this is Linux, I believe, was so small that on this graph that shows the current size of Linux on the far right end, and mind you, this was 2015 size of Linux, actually. So we haven't even gotten to 2018. It's still going up, right? The original size of the Linux operating system when it debuted was so small that it looks like it doesn't exist on this chart. It might as well be 0, right? Yet the size of the same operating system today, which granted does a lot more things, so I'm not saying it's equivalent. I'm just saying what you actually need if you just want to run a Linux system. The kernel has now gotten up to over 18 million lines. And now, again, I want to say this is just the opposite. When I say just the operating system, I don't even mean X Windows. I don't mean the GNU standard library. I mean like just the kernel source tree, which admittedly includes some like documentation and things like this. But this is looking at the lines of code in just the kernel. Okay, so now let's ask the question, because that's pretty bad, right? Let's ask the question, on this machine, how many lines of code would it take to read a text file, right? All I want to do is I want to read in a text file. That's an operation that we might do today, right? And if you think about the way that a modern person reads a text file, they're in a web browser, and the web browser goes to a URL, it downloads a text file, and displays it onto the screen. How many lines of code must be functioning properly and performantly in order for that experience to work reliably and well? The answer is, I don't know, but it's not less than 56 million. I'm not kidding. This is basically what it looks like, right? I picked a random possible way that a website might commonly work, such as a lamp stack, right? Running WordPress. But you could substitute those out with anything else you wanted. They are not particularly high contributors, right? So let's take a look at what I'm talking about here. First of all, you need a web browser. I picked Chrome, but all of them are fairly large. Just to run that web browser is 16 million lines of code that have to be functioning properly in order for your browser to work well and not crash, right? Underneath that, you needed an operating system, and that operating system, I picked Linux. That's at least 17 million lines of code, again, right, that had to be working properly. Now, do all of those lines have to be working properly? No, right? Because obviously there are code paths that will not be lit up when you do this. But since you don't know which ones those are, if you were to ask a person to go verify that this would work okay, that is what they'd be staring at. They don't know which ones are going to be hit by this path, right? They have to start to understand 17 million lines of code's layout, roughly, before they would even know what section to focus their attention on if they want to improve the performance or stability thereof, right? So you need at least Chrome and Linux. I didn't even count X Windows in here, but you probably need at least some substrate. The most minimal version of this probably includes more. That's why this is a minimum bound that I've set, right? So then on top of that, I said, well, there's probably something like OpenWRT running, right? You need your router, the thing that's actually taking the packets off of your Ethernet card and getting them out to the internet, right? That's going to be another 1.5 million lines of code or something like that. Somewhere in there, there's probably a Cisco router, probably multiple of them. Who knows? Probably other routers. I don't know the backbone structure. But depending on the hops between you and the other side of where you're reading the text file, that code is probably many, many millions of lines of code. So we're understating this by a huge amount because all of the OSs of all of the routers and their firmware not counted here. Similarly, I didn't count the firmware of the machine that the Chrome and Linux setup was running on. So then it gets to the other side, okay? And let's say the other side isn't running Linux. Let's say maybe it's running FreeBSD, right? Because that's got a lower line count. So the lowest line count it might be running on the other side would be something like 13 million. But that might be more like 17 million if it's running Linux, or it may be if, let's say, it's running something like Windows or some other custom thing, and AWS on the other side might be on the other side, right? Who knows? Those are many, many millions of lines more. But so somewhere in the order of 10 to 20 millions of lines at least is coming into play there. Then you've got all of the lines of code necessary to run the thing that actually served it to you. And oftentimes that's something like a LAMP stack, Apache PHP, WordPress, MySQL, for example. That's not a very big package even compared to what we're talking about. That's only 7 or 8 million lines of code more. If you had something more substantial running on that side, again, like AWS, something like that, would be way more lines of code probably, right? So again, very conservative, very low estimate of the number of lines of code that you're talking about here is like 55 million, 56 million lines of code. A very low estimate, 56 million lines of code. Okay. So what you can kind of see on here when I highlight what's going on is that over 50% of this problem is coming from nothing other than the part you can't even get rid of, right? So even before, we could spend all day complaining about Apache and PHP and WordPress and MySQL. And we could spend all day having those fun medium.com arguments about how switching to Node.js would have solved this problem or whatever. Forget it. We don't need to have that argument. We don't even need to go there. Because even if everything else, including the browser, went to 0, we haven't even reduced the problem by half. There's still an operating system on either side of this, at least, and several operating systems in the middle, if we were to be honest, right? And they're not going anywhere. I don't care what new web technology hotness you think you're using, you're still stuck with this. Okay. So, let's think about this problem. We are stuck with a giant bloated mass underneath absolutely everything we do, and there's nothing any of us could do about it, pretty much, right? I mean, I'm not going to sit down tomorrow and write 17 million lines of code, right? It is not going to happen. And that's being conservative, right? That's assuming all I wanted to do was do what Linux did, right? Windows is probably way more. It's got more driver coverage, right? And all sorts of things. I don't even want to know. I really just don't. But it'd be a disaster. So is that the way the world works, right? Is that the way the world works? And the answer is it didn't used to work that way. Now this is a picture, although maybe it doesn't look like it right now, this is a picture of like 1,000 operating systems. I'm not even kidding. Because in those days, in the 80s and 90s, generally what happened is every time you bought a new program on a home computer, it came with its own custom operating system whose job it was to run whatever the software was. Because things were so limited, on those systems that all there was the BIOS. You couldn't afford to run another operating system at the same time as you ran a performance-oriented program. When you loaded Doom onto your PC, there was no question that it was going to take over the entire system resources to run it, right? The original Doom, not the new one. And prior to that, in the 90s, in the 1980s, with things like the Amiga computer, for example, every game was a boot disk. It booted into its own customized version of an operating system that ran what it needed to run to make its game work well and be performant and reliable. Right? That's just what happened. So there is no question. We have a clear and obvious existence proof that the notion that an operating system is an unachievable goal, a fool's errand for anyone to attempt to create. We know that that is a consequence of our times and certain decisions by hardware designers and ecosystem maintainers, and not because there is anything intrinsically true about it. We know that in the past, hardware that was very capable and very interesting made it so easy to create an operating system that literally everybody did it. Not a few people, not even most people, but literally everybody. Like, I don't even remember, there's like 3 games I can remember that shipped on the Amiga that ran off of Workbench. Every other thing was a boot disk. That's just what happened. Okay. So now that we're in the modern era, what does it look like, right? Well, it looks like this. This is the best sort of, assessment I could sort of make at the time. And those 2 starred ones there, I think, I was sort of saying they're going away. I was right. They're kind of gone now. But we look at the world of today, there are effectively 3 operating systems that are consumer operating systems, right? So remember, here, so many consumer operating systems, I don't even know how to enumerate them all. I don't even know how many different ones there may have been. Like, I imagine some companies reused the same sort of base OS code that they linked into multiple games, and others didn't. I don't even know how to count how many there were here, though, because there were so many different possible ones. I just can't even start, right? Here, I can put them on one page, and they're on the left. The Windows NT kernel, the Linux kernel, and the FreeBSD kernel. That's it, right? The Windows NT kernel runs PCs that are consumer-facing. The Linux kernel runs PCs that are like, server-based or hardcore, developer-based. And the FreeBSD kernel runs Apple machines. And that's it, right? And then I think also the FreeBSD kernel was the PlayStation 3 and 4. I put that kind of on there, but, and that's it. And it's not even like when we went to phones that we had a bunch of new operating systems. We didn't, right? We just reused these. So the Linux kernel kind of got, Darwin, sorry, not Darwinized, I can't remember the name of, is it just called Android still? I don't know. For making Android, the Linux kernel got repurposed for that. I don't remember what it's called for the bottom. The FreeBSD kernel got turned into Darwin for iOS, right? And for Mac OS 10. And that's just what gets used, right? So hopefully there's no exaggeration in the stuff that I've just said. It really was true that we went from an era of that anyone could program their own operating system and anyone could use a system to its fullest extent. And we transitioned from that in the 90s. We transitioned from that to a world where none of that's true. Basically, no one can make an operating system now. It's a hobbyist project at best. If you do so, no one will use it. You could not ship it as a piece of software. It's out of the question, right? So up till, say, mid-90s, consumer operating system, something that everyone could write. Past the mid-90s, consumer operating system, there's 3. And maybe will never be any more. Who knows, right? We don't know. Still waiting to find out. Okay. So now we ask the question, well, why? right? What changed? Why was this the case? I mean, there's got to be a reason. It doesn't seem likely that we just went from a world where operating systems were a no-brainer to a world where operating systems are something that there's no chance you could ever possibly write. And again, it's just a hobbyist or entertainment or educational or maybe special purpose if you're doing embedded hardware procedure to write one. And you certainly wouldn't do it to ship a game, for example. That's just absolutely ridiculous, right? Well, let me try to suggest some reasons how we ended up here. In 1995, we introduced USB and the concept of plug and play. Now, what this was is it was a wire protocol for serial interfaces, and it was spec'd out to sort of say, well, we don't really know what's going to be plugged into this thing. And so what we'll do is we'll just assume that the person who makes the hardware will do something, right? We don't know what, but we'll do something, and they'll ship a piece of hardware, of software that sits on the other side and knows how to read the something and write to the something, right? And that was USB. In 1996, we started the transition to mandatory hardware accelerated graphics, right? And again, unlike earlier, when I say mandatory hardware accelerated graphics, I mean on the PC. Unlike earlier, when there was hardware accelerated graphics, but it was specific to the platform. So for example, the Amiga computer, the Atari ST, the Commodore 64, all of these had things in them that would do special purpose graphics operations. You kind of needed them to because they were just too slow CPU-wise to do anything if you didn't have something there to help. Unlike those platforms where it was specified what that hardware did and how you might program it, we started introducing a new world where that was no longer true. Instead, you now had mandatory hardware accelerated graphics that you did not know what it was. You had no idea. Could be anything, right? There's just going to be a card in the computer with a graphics accelerator of completely opaque design, and you're just going to have to cross your fingers that there's some kind of an interface somewhere that will allow you to do something with it, and that something will be largely dictated by what the interface happened to spec out and how, right? Very similar to USB. It's like the USB of graphics, basically, right? And if we go back and look at this graph, you can see that there's almost an inflection point there, right? Like the complexity of Linux is going up at a pretty reasonable rate until we hit the introduction of these things, and all of a sudden we're into no man's land, right? We then just shoot straight up the curve, and it's like an exponential curve from that point on, spiraling off into God knows where, right? I can't prove that this is why. There's certainly plenty of other reasons it could be why. But if we think of the simplicity of the platform and the chances that someone could produce an operating system for it as being sort of the wildfire that clears out the forest, if you will, so that new trees can grow and healthy trees can grow, we got rid of that ability. Our forest no longer can have a wildfire. And so now we just cruft on top of cruft forever, right? So, now I'd like to transition from talking about what I think the problem was and why I think the problem is a problem, to asking the question, is there something we could do about this today, right? Is there a way we could go back to an ecosystem that no longer had these undesirable properties that I argue that we now have, right? An ecosystem where, if you will, if you wanted to ship a game that you booted to, right? Like I stuck a USB stick in the computer and I booted into the game. So nothing else was running. Let's say that I am the most hardcore esports person, And I want to make sure that there is literally nothing doing anything on my platform other than this game. And it will have the full system resources with no interruptions and no variability. I could actually do that. I could expect Epic Mega Games to ship me a thumbstick with Fortnite on it that I stick into the front of my computer and boot. Okay? Do we have any chance of seeing that world again? And hopefully I've communicated some reasons why we might want to see that world again. Even if that's not the end goal. Even if what we'd rather have is just some better operating systems, right? The answer is I think there is. And unfortunately, it's not really up to software developers to get there. We can help, but unfortunately, I think it's really up to hardware people to start taking this problem seriously. And here's why. So nowadays, SoCs, which are called systems on a chip, or SoC is the short version, right? SoCs are becoming a very common, very sort of valuable to the product line, even, SKU for many hardware manufacturers. The drive towards miniaturization, cell phones, tablet PCs, the Internet of Things, all of these trends where hardware manufacturers are trying to get their chips into computer devices that are not in the traditional form factor, has meant that there's been a tremendous amount of emphasis placed on integrating components into single modules to eliminate waste. You look inside a PC and you see the motherboard, there's so much cruft on this thing that you'd never be able to get it down into a phone, right? And so in order to legitimately tackle these problems of portable computing and small form factor computing, for very obvious reasons, you need to have all of your stuff shrunk down and minimized and placed into some coherent cruft-free package, right? Well, it's probably not cruft-free, but a lot less cruft, right? A lot of the interconnects and intercommunication needs to be simplified and dropped down in order to get to that point, okay? So this is a very common way of designing computers now. And it's largely because of that sort of drive towards miniaturization. Again, these are not special purpose. They are not embedded computing for some kind of microcontroller in something that controls the water pressure at a sewage treatment plant, right? Which is where you might have thought about this kind of thing before. It's not an embedded microcontroller in that sense. It's literally a consumer part. It's something that goes in your phone or your tablet, right? Your set-top box, your television, your refrigerator pretty soon, etc., right? Because this is now the new standard for consumer devices, well, guess what? It starts to look a lot more like a home computer from the 1980s. All of the chips are designed together, packaged together, interconnected in a predictable way, and there is no configurability. There aren't two possible graphics cards that can be on this die. There's one, right? There aren't 2 or 3 or 4 or 10 different USB controllers that could be attached to this thing. There's one, right? There aren't even multiple CPUs. It's just all baked together. It's all one system. And that starts to look a lot more like a home computer from 1986, right? So my proposal is, what if we were to extend the conceptual model that we have with something like the x86 or now x64 ISA? I consider those things kind of the same thing, right? To cover an entire system on a chip. All right? Now, the reason I make this parallel instead of introducing the concept wholesale is that invariably, whenever you suggest the notion that you might be able to make the design of the hardware interface for an entire architecture robust, predictable, consistent, testable, and known. People act like you're saying you want to go to the moon on the back of a giant turtle, right? It's like you're saying something that's so far from anything they could possibly imagine being true or desirable or possible as to make it ludicrous to even suggest such a thing, right? If you suggest making an ISA, for those of you who don't know what that is, an instruction set architecture is just a definition of how a set of memory layouts, like how a series of pieces of data in memory are interpreted by a piece of hardware to produce a result, right? So a program, an x86 program, that is spec'd to the x86 ISA. You know if you hand it to an x86 chip, it will run, and it will do the same thing on every x86 chip. That's all we're talking about. Right? So if you were to suggest that even to GPU vendors for just the graphics part, it is again like you were traveling to the moon on the back of a giant turtle. So the reason that I liken it here is because, again, I'm not talking about something that is unprecedented or weird. I'm talking about something that not only was standard, but that has been standard for decades, and not only was standard for decades, but proved to be the most valuable resource for the company that controlled it that they ever had. So I think it's time to start revisiting this concept and stop thinking it's ridiculous. Not only is it not ridiculous, it pays so many dividends. And let me talk to you about how that's true, right? Okay. What we're living in right now is a world where the people who create the software and the people who create the hardware are separated by so many layers of additional legacy or modernized software, depending on what part you're talking about, that there is no way to test anything for performance or reliability, period. And I mean that literally. There is no way to test a piece of software in the modern world. The only way you can really hope to get it reliable is by sending it out in the world and fielding the bug reports as they come back. Because there are so many configurations of things out there, there are so many different substrates. Again, 50, 60, 70 is probably low. We're probably talking about hundreds of millions of lines of code in between the thing you wrote, right, and the thing that actually happens on the computer. Contrast this with just straight x86 code that just needed to compute a result. It's 100% reliable pretty much. If you just want to do a for loop that adds some numbers together or something like this, in an x86 ISA, it is almost impossible to have that screw up. The times when there has been mistakes have been few and far between. There's like the Pentium divide bug or things like that are like the only times we have run into problems with that. But in terms of all the rest of the stuff that surrounds that x86 ISA, it's a nightmare. Completely untestable, completely unreliable, completely insecure, completely unmaintainable. It's all of that stuff I showed at the beginning, the crashes, the updating, all of that stuff. That world is unavoidable right now, I maintain, because there's so much stuff in between. What could you possibly do? Shipping reliable software or performance software is very difficult or impossible. Okay? But if we were to lock it down, right? If we were to say no, we're going to settle on a specific ISA. It gets revised every couple of years by making some additions to it, just like the x86, x64 ISA. It goes through revisions every so often, but we all move to them in a wave as they become accepted by the mainstream hardware market. The payoffs would be immense. Suddenly, you could test that something that ran the same on your system would run the same on someone else's system. You wouldn't be guessing anymore, right? You would know, because there wouldn't be tons and tons of variable state software in between in various states of update for various different types of things that interpret things differently, right? Bugs would actually be real bugs in the hardware that would be embarrassing for the companies who ship them, and they would have to introduce actual compliance like Intel does to make sure that they ship things that actually worked. And after that point, any bug that actually occurs is a bug in your software that you shipped. And it's something you could fix and something you could have tested. The user is no longer running a random stack of 60 million lines of code in addition to the 100,000 you shipped. They're just running the 100,000 you shipped. And if it worked on your machine, it works on their machine. Okay. We're already seeing indications of what even tiny steps in this direction would bring in terms of efficiency, reliability, security, performance, all these sorts of things, right? Around the time that I was giving this lecture in 2015, people were talking about Mantle. What was Mantle? Nothing special. It's just a simple way of talking to AMD cards that's closer to what their driver actually was already doing, right? And hey, lo and behold, when you got the AMD driver out of the way, all of a sudden the exact same piece of hardware performed way, way better, right? Here are the performance increases that we're seeing just from getting rid of the Radeon driver. That's all that happened, and not even all of it, just part of it, right? So 50% more performance from getting rid of bad code that sat between you and the hardware. That's all that happened. You didn't buy a new graphics card. You didn't rewrite your engine. You just finally got a chance to program the thing closer to what it actually was, right? Imagine if you took that to the next step and said, look, you don't even need any driver at all. Forget Mantle. Here's just how you download code to a GPU and run it. Again, more reliability. You take code out of the pipe. It becomes more symmetric between the user's machine and yours. The efficiency goes up, the reliability goes up, and of course the security goes up because the less lines of code there are, the less exploit parts there are, right? Every one of those 100 million lines of code, or who even knows how many there are now, in between your app and your hardware is an exploit possibility. Every single one of those can have an exploitable bug in it. Every time you remove one, you are removing a possibility for a virus or a hacker to do something untoward with your system, right? Now that's on the left, the Mantle performance. On the right is a great paper. I highly recommend everyone read it. It was actually came out when I was making this lecture, and I was like, yes, this is what I've been thinking. And basically what it was is saying, hey, what if we just made the operating system be a thing that all it does is broker access to the hardware, but otherwise we let the hardware be almost directly programmable as much as we can. And they could only really do this as sort of a simple test because they couldn't modify the hardware. But what they found was when they made this modification and made sort of a prototype version of it based off of Linux where they stripped things out and made special pathways to test this, they found that the performance they got over straight Linux was dramatic, right? The amount of network processing, that's what they were testing, like network packet processing and stuff like that, that they could achieve over the Linux kernel was nuts, right? Just absolutely nuts. And again, nothing different happened. The computer didn't change. All they did was effectively delete bad code from the pipe. They just got rid of it. And so the benefits to everyone of removing code from a system cannot be overstated. Everything gets better when the code gets smaller, pretty much across the board. So, if we actually wanted to start pursuing this as a real path, right? Going down this road and saying, how do we maybe get to a future where hardware as a rule is designed under a set of guidelines that say, here is the memory that you take in, and here is the memory that you put out, and that's your job. You don't get a driver, right? You don't get one. There's no such thing as a driver. A hardware company ships hardware. You don't get to ship software. If you want to ship software, it's going to have to be on the hardware itself, and we're not going to update it, so it better be really good, right? And again, people freak out at that suggestion. That's what Intel does every day, right? That is what happens with the x86 ISA, right? Or the x64 ISA now. Is it harder? Yes, but that should be the job. That should be what a hardware company is producing reliable hardware, right? And plus, once you demand that as a minimum bar, everyone's on a level playing field, right? If everyone has to meet that bar, then nobody has to worry about the fact that they can't cheat in their driver and do these other things, because no one can cheat. So you pretty much have to just do it. Whatever you're going to do has to be done in the hardware, right? And you're all playing on a level playing field then, because it has to be done in hardware. Okay, so how do we get here? What we essentially need are these sort of 6 points that I've listed here to get to direct coding, right? We need to first get the compatibility, which is speccing out something like an ISA that will be maintained by hardware vendors. We have to have performance reasonable enough that people could start using this for real, right? And why do I say that? Well, you can get your hands on a fully documented SoC today, for example, the Raspberry Pi. There's a few parts that aren't documented, but even the Broadcom chip is now fully documented. The graphics part, rather. There is a little bit of startup code that's not documented, but I think that's the only thing. So you can go get your hands on a Raspberry Pi today and have that compatibility guarantee with other Raspberry Pis, right? But a Raspberry Pi is simply not a good enough piece of hardware for anyone to use it for anything real in a consumer setting, right? You're not going to ship PlayerUnknown's Battlegrounds on the Raspberry Pi. So in order to start being something we could take seriously as a computing platform, it has to be real hardware. It has to be a GeForce 1080 that's made to some ISA. It can't be some old part that nobody wants anymore that just we happen to know how to program. That's not enough, right? Third thing, it needs to be simple, right? You can't just take and say, oh, hey, good news. What we did is we took the GeForce 1080, we moved our entire gigantic driver with all of its programming substrate, and we put it into a ROM on the thing, and now you just send like Vulkan commands to it, right? It's like, no, that's not what we're talking about here. We have to get back to saying, look, we write to some memory, we read to some memory. That's how the interface works, right? It's like it used to be. There isn't some kind of a weird, like, you know, you need 10 million lines of code to access the ISA because that's how much there is or something, right? It has to go back to being sensibly designed. Obviously, we need documentation and tutorials for it so people can learn how to use it and use it well. And then finally, we need some publicity to say, look, this is something people should buy, this is something people should use. So there's a lot of steps to this. It's hard, don't get me wrong. It's a very difficult path to go down because it takes a lot of people to believe it should be done. I don't actually think there's anything hard about it in the difficult to do. It's more about commitment, less about difficulty. But so I kind of split it up here between you, meaning hardware vendors, because that's who this talk was originally designed for, and us, meaning the people who program, right? And have to, you know, would use it. And so I think we split up those 6 things. They break down very cleanly. Hardware designers need to be like actually determine themselves to agree on an SoC, right? An SoC architecture. Then they have to start shipping something, like their really good parts need to follow that SoC, and they need to commit to simplifying the way that it's used to just read-write memory, right? Read-write memory in mailboxes or whatever. That Arrakis paper that I referenced has a really good example of how to do, say, a NIC that just uses ring buffer only hardware interfaces and mailboxes to achieve everything it needs to achieve. That's the kind of thing we need, right? And so hardware designers need to do that. Obviously, software designers can help with that, but they can only help by saying whether or not these interfaces are going to be good enough and simple enough to actually be programmable in a realistic way, but there's nothing else they can do. All the rest of it is up to getting at least one or two hardware developers to actually buy in and try to do something like this. Now, for our part we can do as soon as we have anything even like that, right? We can help with the ring buffer design, like I said. We can help design something that satisfies our need to be able to develop things that are reliable and easy to understand and so on, but that also meet the demands that the hardware has, because the hardware can only do certain things, obviously. But beyond that, we can do everything else. We can make prototype OSs for it. We can document it. We can ship libraries, right? We can make all kinds of libraries that programs could use to run on top of this if they wanted to, so that people who don't want to understand it don't have to understand it. It's always, strictly optional. Things that that look like DirectX on top, or OpenGL on top, or Vulkan on top. So if you already know one of those, you can just program to that still, right? So that there isn't a lot of friction in terms of moving over to it. And then finally, we need a lot of people to be excited about this, but I think we can do that, right? I think the response to Handmade Hero has kind of demonstrated that there are a lot of people who are interested in this sort of thing. They just don't have anywhere to go, and they don't have any way to contribute, right? They don't have any way to help push us towards a future where hardware is something we can actually directly program. Nobody can really do that on the software side of things. But if hardware developers gave us an opportunity to do so, we would. I know I would, and I know lots of people who watch this show would, and I know lots of people who don't watch this show would. I know there's a lot of people out there who want to see something like this happen and would be ecstatic to start contributing to something that could get us there. And so what I think we would do for first steps, right, is to try to get back to the original Linux, right? To try and say, if we were going to start Linux today, the original Linux, I think, was 20,000 lines of assembly code, right? If we were going to redo that today, 20,000 lines of assembly code is something a single individual can write, okay? It's not that hard to do. How do we get to a piece of hardware that has a well enough, simple enough spec interface that you can make the equivalent of the original 1991 Linux in 20,000 lines of assembly language that's just now on a modern part? How do we get there? Because I absolutely do not believe that you can't do it. We just didn't want to. We just kept adding complexity to the hardware interface and adding more and more drivers because that was the path of least resistance. And it was what allowed companies to go off on their own and not have to talk to anyone to agree on how something would be designed, right? That's why we did it. But I fundamentally don't believe there's anything different about today's hardware fundamentally that you couldn't make an operating system in 20,000 lines again if the hardware was designed more sensibly. It could have all the same features it has today. It just needs to be designed more sensibly. And I think we could do that. I think we just look to see, how do we get 20,000 lines of ASM to drive a hypothetical piece of hardware that does what today's hardware does, right? How do we get that? And that's something a hardware company can start working on. That's something that Intel could start doing tomorrow, right? They've got SoCs that have graphics built in. What does the interface to that huge substrate, which I guarantee you takes way more than 20,000 lines of ASM to probably get an operating system up and running on one of these things, right? Why? There are researchers at Intel right now who could answer that why. What is wrong with the design of the interfaces to these chips that they require so much extra work? How do we get it down so that it's the same as Linux was? What can we simplify? Because I know that we can. And then from that answer, we can move on to an initial attempt at an ISA. Something that simplifies the network interface, something that simplifies the SATA interface, something that simplifies the USB interface, something that simplifies the video interface, right? Because fundamentally, all of these things are just the CPU writing to some memory and kicking it off, and then looking for memory that comes back. That's fundamentally all that really is happening here. Why can't we get it down to that? What's stopping us, right? And then I contend once we've got it to something fairly straightforward like that, where you can just look at data definitions and say, you write this data in here and kick it off, this is what the chip does, right? That is very tractable. Any programmer understands how to get that working, right? And it opens up a whole new set of possibilities. Should we keep simplifying from there and keep making it so that we keep getting more and more straightforward and direct ways to talk to hardware and have them do things so that the data that we're actually sending them makes more and more sense and the things they execute make more and more sense? Sure, right? Would it be great if we continue to improve the x64 ISA to make it simpler and more whatever, blah, blah, right? It's always good to do that, yes, but just getting to a place of possibility doesn't require all that. We just need to get rid of the obvious cruft. And I guarantee you 90% of the problem in the way is obvious cruft, not super hard technical problems. All right. So now I'd like to just sort of introduce two possible hypothetical situations, right? I sort of wanted to posit these in a way that would, say, motivate a company such as Intel, for example, as to why, even for a commercial hardware vendor with a vested interest in what they're currently shipping, why might they care about this, right? So the first what if set is negative. What if Linus Torvald had been born 10 years later, right? Sorry, Linus Torvald. Right? Linux would never have happened. There's no way he was going to write a massive thing. Like, there's no way he would have written a system that could have handled like all the USB stuff and all the graphic stuff that we currently do today. No one would want to use this operating system that he started with. It wouldn't be useful to anyone for any purpose, right? So Linux never would have been a thing that took off. And as a consequence, we would literally have a single PC operating system, right? A single one. It'd just be Windows. Every last thing you take for granted right now that was made possible because of Linux would not have happened. All servers would be controlled by Microsoft. All of them, right? Every last thing. Every desktop computer controlled by Microsoft. You would possibly still have had Apple, but it's unclear whether you actually would have or not. Because at that time, again, there was a bunch of other options available thanks to Linux and the ecosystem that it had created. So it's unclear what Mac OS X would have done, and I don't know. So maybe you would have still had an Apple niche, but it certainly wouldn't have been server. And so you would literally be looking at a world where pretty much all PC, but definitely all server, was controlled by Microsoft. Most of what we take for granted on the internet today would not have happened the way that it happened. And with one for-profit company in control of all of it, you have to ask yourself, what would this world look like, right? Number two is, what if there is going to be another Linus in the future? But what if instead of doing it on, say, an Intel piece of hardware or an AMD piece of hardware, what if they do it on something like ARM, right? What if there is a different platform that they pick? Because that platform was simpler, had a more coherent ISA, who knows what happened, right? And the answer is that entire lineage of computing, that entire direction of computing that could develop from that, you will make zero money on. And furthermore, all of the uses that your computing chips would have been doing that migrate to this new platform, you will not make money on any of them, right? No x64 processor will be involved in any of that lineage because that's not where it started, right? So again, the benefits of being the hardware people who start to move in this direction might be very important. And missing out on a trend like that could be very serious. The reason that Intel sells all of their server chips right now is because Linus Torvalds started out programming on an x64, well, an x86, right? That's why. So that whole lineage grew up around that. If it had grown up around something else, x86 would have been the port platform. It would have been like a DEC Alpha or something like that. Who knows if it ever would have taken off? Maybe it wouldn't have got supported. Maybe no one would have cared. And then all of the chips that Intel sells in that market right now, for example, that money just isn't there, right? High margin, very important chips. Nobody wants them. They'd rather have these ARM chips because that's, everyone knows that's what Linux runs best on, is these ARM chips or something, right? Who knows? So then let's get to the positive hypotheticals, which are like, what if we do embrace more of this SoC thing? What are the dividends that could be paid there, right? So first of all, what if making an x64 operating system was as easy as making an application, right? And that's the world of 1980s. It's so easy to make an operating system that everyone who made a game did it, right? If that were the case, think of how many options we would have for defining the future of computing, right? Microsoft's stranglehold on PCs would evaporate immediately, right? Because there'd be so many alternatives that you could never, there'd be no way for a operating system company to sit on their laurels and ship such lackluster things, right? They would get outcompeted pretty much instantaneously. And that's great for everybody. More competition in the OS space means that our OS doesn't have to be so bad like it is right now, right? But it's never going to happen any other way. You're stuck with Linux and Windows right now. That's not changing if the hardware doesn't change first. Okay, so another what if. What if running software on x64 required no OS and they were just tied to the x64 hardware, not to an OS, right? I mean, this is a real possible future. What if the only OS on your system at all was just basically a hypervisor? It was just a thing that switched between full programs that just ran directly on top of the hardware, right? Now, all of a sudden, x64 is king of the hill. Right now, Windows is king of the hill. It doesn't really matter that something's written for x64 anymore all that much, right? It matters that it's written to the Windows APIs or the browser's APIs, right? That's what matters. That's what determines what runs where, okay? And it determines, furthermore, who has the entrenched advantage. x64 chip vendors have an entrenched advantage of running x64 code. How much of that is there out there? Not that much anymore. Why? Because it's not the hard part of the problem. Producing the CPU code is not the hard part of the problem. It's all the drivers, it's all the infrastructure necessary to run the rest of the hardware, the mouse input, the keyboard input, talking to printers, all that stuff, right? That's the thing that actually determines who controls the ecosystem, is that substrate. And increasingly now that's like W3C, right? And that makes x64, or whatever your hardware part is, irrelevant. Nobody cares what you spec, and nobody is enticed to run on your platform because who cares? As long as someone ported the web browser, you're done, right? So if a group of hardware developers did go in this direction, it could pay enormous dividends because they would be the people who would be able to sell the chips. And people not producing chips that comply with this ISA would be at a massive disadvantage. There are huge potential payoffs for going this way early if it did take off, because now you're in a great position to be the leaders in shipping things that comply to this ISA, right? Because as software gets written closer to the ISA, you become the platform, not the W3C, right? Or whoever else it happens to be at the time. So it's actually very good for hardware people. It's a very advantageous position. And furthermore, it's something that allows you to provide real gains to your customers. Right now, if I was someone working at Intel or AMD, I'd be pulling my hair out because I'm like, the only people I know how to get any performance improvements to are like game developers, right? There's nothing like this web browsers and that spec is such a disaster. There's nothing I can do, right? I shipped someone this new Core i9 chip and it's just as bad as experience as if they were running on an i3, right? It doesn't matter. Because there's so much cruft in the way and it's so divorced from the hardware that it just doesn't matter. I can't really help you, you know? I can't really provide those real performance gains because it's unclear what I would even target at this point, right? Whereas if things are directly running on an x64, you can have this power to ship huge improvements every time because the software is literally just running on top of your stuff, and when you improve it, everything improves. And the things that people can ship that year are twice as good as the things they could ship the previous year for reals. And that's not a world we've been living in for a very long time, except on basically GPU code for games is really where the only place we've been seeing that, right? And finally, as a positive hypothetical, for companies like Intel or companies like Samsung, you've got great fab technology. What if that was what determined market leadership, right? We all know we're going to be using this ISA. So wouldn't you like it that the person who builds the best hardware wins? Isn't that the best, right? Whereas right now, you're rapidly moving towards a world where nobody cares for consumer operating systems. Nobody cares. I don't know which chips in this computer, don't care, right? Or whatever, is what most people would think. They really just can't even perceive the difference. A lot of times now you buy a new laptop, it feels exact the same as your old laptop, right? That's no good for a hardware company. What are you going to sell people? How are you going to convince them to upgrade, right? These are real problems. You need to make ways for people to program and use the hardware for real, because simply increasing the clock rate doesn't really work anymore, right? We've passed that heat point. And so you need to offer your customers something. We can help you offer customers those things if you actually give us a way to program the hardware for real. And again, just look at the console market to see that that's true. Game developers who work on console hardware do amazing things with that hardware that is so much better than what they could do with the hardware normally, because they can exploit all this stuff, because they know effectively the ISA, right? So that's the end of the talk. I hope that gave some perspective on what I think the problems are, why I think they're problems, and what could be done to fix those problems. But in short, the TLDR of it, right, is just we know we have a better opportunity because we had it in 1980, right? We had it in the 80s. We lost it in the 90s, and now we're living in a world without it. I think we can get back there, and I think there are real reasons we want to. For everyone's sake, not just people who love computing and who love hardware-oriented programming, but just the ability to unleash all of the people who care about that kind of programming, to let them actually start doing real work again. Those people will produce the libraries and the system services and the documentation and the tutorials. They'll produce the substrate that will allow everyone on top to excel. So it doesn't even matter that it's only 10% of the programmers who can really do something down there, maybe, because it's really a type of program that only certain people enjoy or certain people are good at. Even that's okay. Because those people just need to be given the chance. And we've already seen that they will, much like Linus did, share what they create with the world in beneficial ways. But right now, they cannot do that. They cannot help you. And I think you really do want them to. And I don't think it's just altruistic. I don't think it's just sort of a fanciful thing. I think it could pay real dividends, both in terms of the quality of the computing experience that we will have in the future, but also in terms of real, actual monetary benefits for commercial companies if they were to go this route. If even a small consortium of major hardware vendors decided to go this route and start shipping a platform with a stable ISA that people could directly program to, I think it wouldn't take more than 5 to 10 years for us to really start seeing real dividends from that thing. All the way from that being the new obvious answer to things like consoles and set-top boxes, so I think you get major design wins there, but just to the fact that it could usher in a real revolution in real home computing, that we can't even predict how many positive outcomes there may be from it. Positive outcomes like the one we had when Linus made Linux, that has, I think by anyone's estimation, radically changed the face of computing for the better, because without Linux, I think we would have been living in a much worse world. I don't think Linux can happen again without hardware vendors changing the way they do things, and I think for all of our benefits they should. I want to see Linux happen again, and I think they can make it happen. So please consider it, and know that there's tons of us out here who are ready to help you and jump on that bandwagon if the time comes. So thanks very much for listening, and I'm happy to take questions now from the stream. Arif asks, is include OS going in the right direction? It does not contain the OS, only your program, except for a bootloader. I have not looked at it because I did not know about that, but from your description, it sounds exactly like the kind of thing that I'm talking about, right? And similarly, like hypervisors are sort of in this direction as well, in the sense that, like, although they can't, because the hardware underneath is too complicated, they can't really provide the kind of thing that we really want for a consumer experience where it has the full capability of running a graphics driver easily and all that sort of stuff, right? They kind of only solve like a little bit of the problem, but they are going in that correct direction in a sense, right? Vitefrafau, did you have any returns since you made that talk? So I only gave the talk to a very small number of people at Intel. It was well received, and I did end up talking to a vice president there about it. But at the end of the day, what I sort of gathered from it was that in order to really ever get something done at a major hardware vendor, you need to create a really big public demand for something, which is why it's like, let me just give this thing publicly. I've been meaning to do it for a while. And the reason I said it is just because they have so much riding on their hardware and it costs so much to produce that even if something sounds like a good idea and they agree with it, it's unclear to them that they can generate the kinds of internal momentum necessary to get it to actually happen. And I don't fault them for that. I think being a hardware company is not like being a software company. Being a hardware company is you must be very risk averse, because fabbing a chip, designing and fabbing a chip is an incredibly expensive process on the order that we cannot really comprehend in software because we don't deal with it day to day. And so they are right to be cautious, and I don't blame them. But we need them to go in this direction, I believe. And so the question to me is, how do we generate the momentum inside their companies to make it happen? How do we help them generate that momentum? Because it's not their fault. It's not like, even if we all agree this was right, it's not their fault it's not happening. Because they need market pressure, they need external pressure, external demand to become obvious to lots of people at that company before they can really put those initiatives in The reason I say it's a collaborative effort is in the software community, we need to figure out ways we can start to really articulate why this is important and show the demand needs to be there and show what the roadmap looks like, because hardware companies can't just do this on a whim. They can't just go, oh yeah, I saw that talk by Casey Muratori, sounded like a good idea. Let's go simplify the interface and put out a chip. It's like, that's not the reality of hardware, right? So I do think it was received well, and I do think it will be received well at hardware companies. I just think it's not that simple. The people at the hardware companies who agree with it can't just start doing it. They need a lot of buy-in, and they need a lot of external, obvious buy-in. These are publicly traded companies with a lot on the line, with incredibly expensive processes that they can't just dedicate to, sort of a pet project that people think is good. Have I seen Redux OS and it's 20 KLOC Minix? Again, I want to be clear about the 20,000 line thing. It's not that hard to make a small x86 operating system or x64 operating system in 20,000 lines of code, right? It won't do anything, right? It won't run a 3D game. It won't support most printers or keyboards or video webcams, right? Because all of that stuff is the cruft. And so making an x64 operating system that's just running x64 code that doesn't interface with any external devices, or that still uses the VGA aperture to draw a console, hasn't gotten any harder since 1991, really. x64 is nominally a bit harder than x86 to get started up, I believe. But it's not really that much different. So OSs right now that are 20,000 lines of code, but that don't have running 3D graphics at full speed, blah, 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 right? Like all that stuff. That's the hard part. The hard part is getting the consumer parts in there. And so that's what the thing is that we need to focus on, is that part, right? So I just want to be clear on that, because there are small OSs out there that don't really support modern consumer features. And that's the problem. What can someone who isn't a hardware vendor do towards this cause? I think, again, it's about us trying to create and publicize this sort of understanding of the problem. Understanding that a 30 million line at minimum barrier between a developer and their user is not tenable. And that the reason our computing experiences today are so bad is because of it, right? I think sort of pushing this narrative forwards and understanding that this is a problem that needs solving, and we need hardware developers to help us solve it, I think that's what we can do as the first step. And once we start getting people thinking it's a problem that needs to solve, then we can move on to thinking about how we solve it. But right now, I think the problem is almost a meta problem. People need to start understanding how bad this situation is. They can feel it, because when you use a PC today, it's a nightmare, right? But we need to start articulating why. And we need to start articulating the path forward. And so that needs to start happening. What about security? Should that be part of a new OS or built into hardware somehow directly? So I would actually argue that security is something that actually can be made much more robust in the world that I'm talking about. And here's why. Let's suppose we go to a system that's very similar to the 1980s system, right? Where, and this is a hyperbole, I don't think this is where we want to end up, but I'm just going to give you an example. It would have been incredibly difficult to write a virus that attacked a game on the Amiga computer, because every new game was completely different and ran in a very different way, right? So the viruses that typically attacked that computer actually had a much harder time with anything that was doing a custom OS. The things that it tended to attack were the standard OS, the Workbench one that shipped with it, right? And so I think in today's world, I think there's a real parallel to that. Let's suppose that you had a separate way of writing to the disk and a separate way of, like a completely compartmentalized, wholly run thing that the ISA just boots to, right? That is the web browser you use to go on and do your banking. And when you want to do something else, you boot out of it. It's gone. And nobody even knows what the that segment of the drive isn't even accessible to anyone else, because that segment of the drive was written by that thing, and it's the only thing that even knows where it is or what format it's in or whatever, right? That is actually a world where security breaches are way harder than they used to be, because now you have to deal with so much variability. You're essentially making the virus writer's task way harder, right? The more compartmentalized you make a program and the less things it uses and relies on that are known to be standard, the harder the virus author's job is. So actually, I would say that all of the security problems we have today, in a new world like I'm talking about, we would already get way less even before we started talking about what to do in addition to them for security purposes. Because not having everything run on a giant, essentially 60 million line exploit target, right, removes a huge number of the potential ways people break into systems. So that's a great feature. It's not all we want to do. Yes, for security, we'd want to start thinking about how do you make that ISA be as secure as possible by design. But I think even before you start doing that, you've gotten into a better place than we are today. Oops. Will this talk be uploaded on YouTube? Yes. IncludeOS runs on C++. What about programming languages issue? I guess I'm not sure what you mean about that stuff. I don't know much about, I don't know anything about IncludeOS. But what I was going to say is, I don't think programming languages are an issue here at all. The benefit of an ISA is it is an ISA. It defines the memory format for the things that the hardware can do. And so any language can now compile to it. It's the same as x64. x64, it doesn't matter what programming language you use. Do you want to use C#? Great. Do you want to use C++? Great. Do you want to use ML? Fantastic. Do you want to run in JavaScript? Well, you're going to need an interpreter, but no problem. That interpreter can run on x64 as well, right? Do you want to use Go? Go nuts, right? And so I think that an ISA is great because it just says, here's what has to happen data-wise in memory. And with this is what the data has to look like in memory for the CPU, the SoC to do things. And I don't care how it got there, right? You can do whatever you want. You can get that data, you can produce that data from any utility you want. And so every language can support it if it wants to. Any language that wants to make a backend, you know, Clang can just make a, LLVM can make a backend for it, and then anything that Clang can take can do it, right? Have I had a chance to evaluate Agner Fogg's ISA? I haven't, but I don't think that's the kind of ISA I'm talking about. I think that's just an ISA for CPUs. Am I wrong? I don't think it's for the system. It's the system that we need. I don't think x64 is fundamentally a problem. Are there things you'd probably change about x64 if you wanted to make it better? Absolutely. Do I think that's the problem? No. It's very stable. We can use it. I don't think it needs a lot of modification. It's not the big part of the problem today. The big part of the problem today is all the stuff that's not in the x64 ISA. How the USB controller is programmed, how the graphics controller is programmed, how the, trying to think if there's anything else in particular. I don't think there is. I think if you had the USB and graphics controller, you'd be pretty much a pretty far bit of the way there. But For smaller code, you need reusability, and for reusability, you need generic programming. Programmers are not used to writing generic code, and companies don't care about reusability as long as they ship features. Do you think generic programming should be taught in practice more? I disagree with that, just even the premise. Generic code is usually larger, not smaller. Smaller code is usually because it was specific, right? And so I think the important thing to understand is like, hey, in the DOS days, if you wanted to initialize the graphics card, you put 2 values into 2 registers and you triggered the interrupt. That is setting up the graphics card. Nowadays, you need to make like 1 billion OpenGL calls, right? Or Vulkan calls or whatever, right? That sort of conciseness of the programmability is what leads to the problem. And it's not really about generic programming. Can you give an example of how the interface would be simpler for your common programmer? Sure. That DOS example I just gave is a very good example, right? Initializing something by doing 2 mobs and an int is so far removed from how you have to initialize a graphics card today in terms of programmer time and energy that it's insane, right? And the problem hasn't really gotten that much harder. I know people think it has, but it hasn't really. Especially as GPUs become programmable, a lot of what you do with them is just uploading bytecode for them to run, right? Not bytecode's the wrong term, compiled, code for their machine language, right? And the control of them is not that complicated and could be simplified further. If we got back to that, that's all you would do when you needed to initialize a graphics card. You wouldn't need tons of libraries and drivers and all these other things in your way. Because fundamentally speaking, it's just not that hard of a problem. Not much harder to set up 64-bit and 3-bit, just one more step. Yeah, I mean, like I said, it's very minor, right? You just have to do a little bit to get yourself into 64-bit mode. And yes, the talk will be watchable on YouTube. Internal static void. So do you propose that we should make a chip that doesn't support computer features or features that a consumer expects? No, what I'm suggesting is we need to just take... So for example, we already have chips that are almost what we want, right? So for example, a lot of laptops that consumers actually use today have their CPU and their GPU supplied by Intel on a single die, right? The Core i7, for example, had the GPU welded onto it, and it's got a known programming ISA on it, right? The difference is that ISA is not stable from generation to generation, and it's not particularly well designed. But fundamentally speaking, that's already what we're talking about. A Core i7 chip was almost what we need hardware-wise. It just wasn't necessarily designed at the interface level to be something that's particularly usable, but it could have been. Do you think that maybe the reason that some of the software and driver has become more bloated and some of the code paths are larger is because the hardware is more complicated than it used to be as well? No, I actually don't think that's true. I think the hardware is actually simpler now than it used to be in a lot of ways. I don't think that you can look at something like an Amiga computer and think that it was particularly simple. It was still rather complicated, and programming it well was actually pretty tricky at some level if you really did want to get it. It was a fairly high point in programming complexity. I think nowadays GPUs are actually very programmable, and a lot of what they do just looks like executing machine code like a CPU would do, right? It's not that special purpose. And that is why I think we're getting... I wouldn't have recommended this path in the year 2000 because things were still so tweaky special purpose and changing so rapidly that I don't think it would have made any sense to settle on an ISA. Nowadays, GPUs are becoming almost just other CPUs, right? And I think if we just started to look at it as a unified ISA, it actually can be quite simple, even compared to old computers we used to program directly. And again, that's only because we have gotten to a place where these things became general purpose because they had to in order to support the kinds of workloads we wanted, right? They are continuing, as we go, GPUs have steadily gotten less and less like it. They used to be very much like an Amiga chip. All kinds of crazy special purpose stuff, right? And that's all they could do, no general purpose, right? And as they go, they've gotten much simpler. And when I say simpler, I don't mean in terms of their capabilities. I mean in terms of their difference from an x64, right? A modern GPU is now very close to an x64 chip. It used to be nothing like one. And standardizing on an instruction set for one might have been a really silly idea at that time, right? So I think that it's really, that's not the explanation. I think the reason that software and drivers come overloaded is because of the route we took to get there. And make no mistake, it may have been necessary to go that route. It may have been very good for us to have a time in computing history when it was crazy cruft in between mushy, almost barely working stuff that anyone could swap in and out, because that allowed the hardware to experiment a lot. And we needed that. Until we started realizing that GPUs are going to be basically CPUs, we needed that, right? But now that we're kind of starting to converge, I think the time has come to start looking towards an ISA again, right? So I don't think, I'm not trying to make any arguments that we did the wrong thing then. Maybe it was the right thing for its time. I think it needs to come back around. Does the world you're promoting mean the end or at least a big decrease in interoperability? If so, wouldn't that make developing applications much harder across multiple systems? No, it means the opposite of that. The reason I suggest it means the opposite of that is, for example, take the current situation today where you want to ship a game on a PC and on a Mac. Right now, that is an incredibly difficult proposition, actually. Most people who want to do it do absolutely ridiculous stuff to make that happen. Either they use a huge abstraction library to separate them from the problem, and that abstraction library has two totally different compilation paths, one for Apple and one for PC. Or they do hilarious things like use a DirectX emulation layer on their Apple part that silently transcodes it to metal, right? So the interoperability is actually awful today. It's very, very bad. You pretty much need two completely different executables for Apple and PC. What I would point out, it's the same computer. It's the exact same computer. You got the same GeForce card and the same Intel chip in the Apple computer as you have in the PC. Yet you need a completely different program on both to run. If, on the other hand, the ISA was on the hardware level, you'd just ship the same program. Both OSs could just run the same program. You'd be done, right? Interoperability would be a little harder for things that want to use a window manager, so non-full screen. But for games, you'd just ship the same package. Every game that shipped on a PC would just run on a Mac. You'd be done, right? So actually, it's the opposite. Having a hardware ISA can only increase the chances that you will be able to interoperate, not the other way around, because the world we live in today is the one where you have no interoperability. And the only way to get portability is to run on top of a huge stack of libraries. The world I'm talking about, you can still do that. You can still run on a huge stack of libraries if you want to, right? Because it's the same, you could. But you also now have the option of not doing that. And it could run in multiple places even when you don't. So it's, if anything, increases the interoperability. It can never decrease it. Because you always have the option of doing what you did before, which is just have a huge pile of libraries underneath you. So if you want that, you can still do it, right? Nothing would stop you. Isn't that what Android and I believe iOS do? Sorry, I'm not sure what the thing is that you're referring to. Probably because it was asked a while back. In a world where every program runs its own OS, how do you handle running two programs simultaneously, or am I misunderstanding? So you may be misunderstanding slightly. Again, what I'm suggesting is not that we need a world where everyone writes their own OS, because you don't really need to do that for any particular purpose, and it's totally fine to write something that isn't running on its own OS, right? But there's two answers to that question. One, if we do want a world where every program runs on its own OS, we can do that using something like a hypervisor, right? That's what a hypervisor is today. It's how data centers work, right? It's how things work where you have multiple OSs that need to maybe run on this shared computing device that time shares depending on who is loaded on it at the time. So we have a solution to that problem. It's ring -1 in an Intel chip or whatever you want to call it. We have a solution to that problem, so we can run 2 programs simultaneously or more if we want to and swap between them based on which one we're trying to use. But I'm not even advocating that. I don't think we need a world where every programmer writes their own OS. It's not necessary. What I'm advocating is a world in which anyone who wants to write an OS can, right? Because that's how we get ourselves out of this world of very restrictive, poor performing OSs that have to be huge as well and are very unreliable, right? So being put in a position where we can innovate on OSs easily and also where the OS itself is not thought of as a big deal, right? It's just, oh, what OS are you running out? It doesn't really matter that much, right? Because the services the OS provides are very minimal at that point, right? Right now, the services the OS provides are imperative and maximal. Without the OS's graphics drivers, USB driver, disk driver, network driver, without all that stuff in place, you can't even make a barely functioning program, right? But in the future, when you didn't need any of those things, the OS isn't really that relevant. And you could run the same program potentially on many different OSs without it being a big deal, for example, right? So if we were to move towards more of a hardware specified world, it just opens up a lot of possibilities. And you don't have to use those possibilities everywhere. Having them be available, though, is critical. And it's critical for that competition and experimentation. So you propose there is no multitasking because if you start separating applications, you will start to get all the requirements of modern operating systems over time. So yes and no, right? There's a couple of things that I would point out about that. One is that at the moment, people make very low use of multitasking. They make such low use of multitasking that things like Android and iOS support it in a very light and restrictive fashion, right? So if you look at how people actually use their systems, multitasking is not as relevant as you might think. But let me put that into some context here. To the extent that you want multitasking, at least for example, the way I use it, is usually partitioned. It's partitioned into 2 things. One, there are background tasks that I may want to run, and then there is the application I'm actually using, right? And to a large extent, that is all I really want my hypervisor or OS to do, right? Maybe I want to download something in the background, but other than that, I really don't want my computer to be doing anything other than what I'm actually doing right now, right? So there are some things you may want to run in the background, and then most of your computing resources you want to be devoted to one thing. Getting to a place where that is a more sensible thing, rather than the current mode of multitasking, where there's just tons of crap running on my operating system at all times, I would actually say a more restrictive version of multitasking would actually be a good thing. That said, that's my opinion, and I don't think my opinion is the important part here. Having different OSs for different purposes is what I want. I want an OS that works the way I just said, and I'd love you to have an OS that works the way you want, right? Getting down to an ISA where a program can be written without thought to the OS it was running on would be a huge win for that, right? Because furthermore, you could have a sort of standardized OS layer, a minimal one on top of that we could innovate on, whereas any OS that, something like POSIX, right? If you wanted to make something that was like the new POSIX, here is a standard, we architected it well, we really thought about it, here's the thing you can write applications to that's the minimum library necessary to talk to an OS, right? And then everything that's hardware related, you can just do directly to hardware. We broker it a little bit, but that's it, right? Much like Arrakis, that paper I referenced, please read it. It's very good. If we did a minimal thing like that we all agreed on, then everyone could write OSs that ran everyone's software, right? Because now there's no chance of that, because there's so much disagreement about how you would even drive the hardware that there's no chance of it. But once you take all of that out of it, you realize the services an operating system should be delivering to you are so small that we could just probably agree on them in something like POSIX. Again, how do I know this? Because we used to do it. Back when hardware was designed sensibly, we had stuff like a fairly small substrate of how you would do things. A VT100 terminal spec was all you really needed, right? I don't think we're fundamentally that far away from that. I think we've let ourselves get that far away because of the driver nightmare. But I think we can move away from it. And once you move away from it, you start to lose a lot of these compatibility issues that you're talking about. Heads are really cute. So all we really need is for USB to be in the ISA and CPUs with enough cores to be GPU for the GPU to run. We don't even need that, right? You can have a CPU and a GPU. Just make the GPU be a standard programmable spec that stays compatible as you move forward. That's all we need. We don't need to replace GPUs. GPUs can still play their purpose. You can have a heterogeneous computing environment. Again, the Amiga was a heterogeneous computing environment. It had a CPU and a GPU and an APU, an audio processing unit, right? And so it's not at all about removing the GPU from the equation or removing USB from the equation. It's about standardizing on interfaces to them that are hardware based and saying we're going to accept the limitation of that going forward, right? And so the x64 and x86 ICEs are examples of how that worked for us in PC computing. We never got one of those for a GPU. Let's try to get one. And while we're at it, let's get one for the USB controller and the disk controller as well. Because if we have those, then you can make an OS very easily. We could do handmade OS and it would be, 30 episodes long or something, right? If we did it now, it would be God knows how long. It would go on forever, right? To try and get all the stuff in there. Do you feel there's a risk to locking things into an ISA that is potentially still substantially evolving? The average lifespan of an ISA should be substantially longer than an API, and I worry that the rate of progress would necessarily change for the worse. So that's a judgment call, and I think you're exactly right, so I do not disagree with that at all. I think it's a judgment call when you want to move from an API to an ISA, right? I'm arguing the time is now. I'm arguing that we have crossed the threshold of where the problem is no longer the hardware innovation, it's the API. It's the cruft, right? My argument is not that there aren't drawbacks to switching to an ISA. My argument is that they are now less drawbacks to that than there are from continuing the path we're going. So it's a switch, right? For a while, it was probably clearly the right decision not to lock into an ISA for the entire system. I think we have gotten to the point where now that trade-off has changed. I think the computing world would be better served going forward, and the future would be brighter if now we said, we know enough about these problems now that we're willing to take the hit, and it is a hit, of switching to a reliable ISA going forwards. Internal stack void. The Amiga GPU was just a wire that went across the screen. What are you talking? No. No. The Amiga had two separately programmable graphic-specific units. One was the copper unit, and maybe that's the one you're referring to, which is the wire that goes across the screen. But the other was the blitter, which is a programmable memory movement device that could also do raster ops on it and barrel shifting. And they had to be programmed separately. It also had a separate audio processing unit that you programmed separately. And yeah, just again, Specialized memory, also in the Amiga. The Amiga had two types of memory, fast RAM and chip RAM. I won't go into the specifics of it, but it was because of the access patterns. They were on off clock cycles. So one was, it was called fast RAM because the CPU didn't have to share the memory bus with the chips for that memory. So the Amiga also had segmented memory. There was memory that could be accessed by GPU and memory that couldn't be. So again, exactly the same. You are drastically oversimplifying your model of what the Amiga architecture was. Is Arrakis part of the Dune OS? I'm not sure. All right, I think we have come to the end. I think we have come to the end of the lecture. Just looking at the chat real quickly, I would summarize what some of the people are saying. Obviously, yes, switching to an ISA does not stop innovation. You can still innovate on the ISA as you go forward. It does slow it down. The reason it slows it down is because people have to agree, and agreeing on things takes time, right? Right now, NVIDIA, AMD, these companies can do whatever they want under the hood to a certain extent, right? And so forcing them to now comply with some level of specificity in terms of what their hardware takes in, it reduces some of their ability to change things. That's all. So, you know, that's what I would say. Obviously, the ISA, yes, it does not prevent you from innovating. The x86, x64 ISA has been revved many times, right? And they've added, I mean, they added SIMD to it, right? It wasn't even a SIMD processor at first. They added SIMD, they added multi-core, they've added lots of things to the x86 ISA. So yes, innovation still occurs, it's just a little harder, right? And so you don't want to switch to an ISA until it's clear that the benefits of switching to it are better than the drawbacks. And I'm arguing that they now are, whereas they once probably weren't. Oops. Got some other questions here. The Amiga didn't evolve since 1985. Why do you want to freeze PC into 20? So that's that's a totally incorrect argument. I mean, I apologize, but it's laughably bad. The reason the Amiga didn't evolve since 1986 was because Commodore canceled it. They had another chipset architecture. It was a 256 color architecture, actually. It was much better than the one that they had. The one that they had was a 32, charitably 64 later with half-bright mode architecture. The 4096 color thing is a different thing. Don't worry about that. But they had an 8-bit per color architecture that was ready to come out almost immediately after it. And Commodore canceled it because they just didn't want to pay for that stuff. They weren't interested in that stuff. So that was really a corporate problem and had nothing to do with an ISA. The reason I say it's a laughable argument is because we've had an ISA in the PC space. It's the x86 ISA, and it's gone through many revisions and added so much stuff that the design of a PC CPU today is nothing like it was when that ISA was introduced. So switching to an ISA absolutely doesn't freeze the design in any way. You still update it very regularly. The difference is just you lose a little of the speed of your innovation, right? You can't just go about it willy-nilly anymore. Are you still in contact with Intel about this? No, I'm not. That I know of anyway. I mean, I don't know what they're doing about it, but I have not talked to them about it in a while. So. All right, that's it. So I'm going to wrap it up now. Thank you very much for joining me. And I will post the lecture on YouTube for those of you who are interested. I will be back tomorrow with our regularly scheduled programming. Take it easy, everybody.